Good morning, all of you. In today's session, we are going to start with the 10th standard chemistry and physics, unit number 8, chemical bonding. Series number 13 is going to be discussed. Earlier, we completed how the chemical bond formation is possible, what could be the criteria for ionic bond formation, covalent bond formation, and the Lewis dot structure, Lewis Kochel theory for electronic theory of valency. All these things were explained and all detailed explanation available in the channel called World of Competitive Chemistry. In addition to all these, unit 1 to 7, entire detailed explanation available on the channel World of Competitive Chemistry. Now we entered into series number 13, which is the advanced theory. Whatever obstacles we faced in the Vesper theory, Valency bond electron pair repulsion theory. So those obstacles overcome in this theory called Valency bond theory. So we can assume this is somewhat advanced when compared to that Vesper theory. Let us discuss about this Valency bond theory. And the Valency bond theory mainly focus on hybridization of orbitals. Hybridization is defined as intermixing of all different kind of orbitals into equi-energetic, equi-sized, equal degenerated orbitals is named as hybridization. For example, if we are mixing one s orbital with one p orbital, so leads to give the sp hybridized orbitals. One s orbital get mixed with two p orbitals, sp2 hybridized orbitals will be originated. We are mixing s orbital with a 3p orbital so that sp3 hybridization is possible. We will get the tetrahedral geometry in this manner. Hybridization denotes the mixing of orbitals, which leads to the formation of hybridized mixed orbitals. Initially, one of the orbital, s orbital in the spherical, p orbital is the dumbbell. When we are mixing these two, corresponding orbitals are in the equal energy as well as equal dimensional shape. That is the main criteria of hybridization. Now, let us apply this valency bond theory for various molecules like a beryllium dichloride. Already we know beryllium dichloride is a linear molecule. Then how could be the hybridization is possible and what will be the structural features for this compound? So beryllium being it is atomic number 4, electronic configuration is defined as 1s2 and 2s2. It has no unpaired electrons on it. All are got paired. It is expected not to form the covalent bond. So covalent bond formation may not be possible if this is the condition. But so when we are exciting this molecule, it will participate in the bond formation with the 2 chlorine atoms, so that here the orbital degeneracy will be lost and the 2 electrons from this s orbital will be excited into those 2 electrons excited into 2s1 and 2px1. So here already 2 electrons are present in s orbital. One of the electron entered into 2px, so that it is converted into beryllium with 1s2, 2s1, 2px1. That means 2 electrons available for bond formation, sharing of electrons. So that each chlorine, already we know each chlorine is a short of 1 electron in order to achieve the nearby noble gas configuration called organ. That's the reason why. So here beryllium being it is 2 electron system, that means 2 electrons for sharing system. Here 2 chlorines are required here. That's the reason why beryllium binds with the 2 chlorine atoms, and there is a formation of molecule in this manner where beryllium will be the central atom and surrounded with the 2 chlorine by mutual sharing of electrons, and it is appeared to be a linear molecule. For all linear molecules, the bond angle is assumed to be 180 degrees. Half of the circle got completed. That's the reason why 180 degrees will be the bond angle for when we are taking beryllium dichloride. What kind of hybridization it will participate? sp hybridization. One of the s orbital of where we are having s orbital, 2 s orbital is there, and 2p x orbital is there. That means 1 s orbital, 1 p orbital got mixed in the equal proportion, so that here sp hybridized orbitals got generated in the linear fashion, where they get mixed with the 2 chlorine atoms in the individual form, and there is a formation of a hybridized orbital got mutually sharing electrons with the chlorine atoms, and a linear molecule got generated, and whose bond angle is denoted as 180 degrees. Now, formation of beryllium dichloride, what will be the chemistry involved in this? Let us discuss. A beryllium formed two covalent bonds with the two chlorine atoms with the sigma 2s and 3p due to the overlap of 2s orbital of beryllium with the 3pz orbital of chlorine atom. So they are sharing electrons, and the overlap of 2px of beryllium is possible, and 3p orbital of the chlorine will participate in this kind of bond formation. Here in the sigma bond formation, 2p orbital of beryllium and 3p orbital of chlorine is participating in the mutual sharing of electrons. As the orbital overlap is different, the bond strength of beryllium chloride must be different, but both the bonds are having equal strength. Actually, here what we are observing, beryllium with s orbital, beryllium with a p orbital, if participate in the bond formation, what happens? A different strength of bond should be generated. But practical observation, what it is showing, exact equal strength containing two orbitals are there, equal to same strength containing orbitals are there, and equal bond angle is also assigned in the both ends of that bond. That is purely because of hybridization of orbitals. Hybridization is the concept which is given by the scientist called Linus Pauling in 1931. Linus Pauling mainly given that hybridization is nothing but mixing of atomic orbitals leads to give the equi-energetic, equi-sized, and also equi-shaped kind of orbitals, which used to give the uniform bond angle, bond lengths. So there is a uniformity will be observed after the hybridization of these atomic orbitals, the concept given by Linus Pauling in 1931. Here, hybridization is the phenomenon of intermixing of atomic orbitals almost equal energy which are present in the outer shell of the atom. Their reshuffling or redistribution into the same number or orbital, but with the equal properties like energy and shape. If one s orbital with a p orbital got mixed here, we will get the nature of the bond with the linear. If s orbital with the two p orbitals got intermixed, then there is a formation of a trigonal planar geometry with the three lobes. If you are mixing one s orbital with the three p orbitals, what happens? The hybridized orbitals are acquiring the geometry of tetrahedral. So four bonds are occupying four corners of regular tetrahedron. So this will be the intermixing of orbitals and giving the hybridized or mixed orbitals which are having equal energy and dimensional shape. Beryllium is in its excited state, 2s orbital is acquiring one electron, and 2px also associated with one more electron containing unpaired electrons on it, and they will redistribute it by intermixing of all these, and identical orbitals are generated. As per the Hund's rule, the orbitals, each orbital should get one electron, then only pairing of electrons are required. That's the reason why 2s with after mixing of all these s orbital, sp hybridized orbital with one electron, any other sp hybridized orbital with any other electron is possible. New orbitals based on the type of orbital that have undergone with the hybridization called sp hybridization. Here, two sp hybridization hybridized orbitals present on the beryllium got separated by the bond angle with 180. Being it is linear, always linear geometry will assign the bond angle 180 degrees. Each chlorine atom comes with a 3pz orbital with one electron in each. One electron short will be there. That's the reason why they will contribute towards the mutual sharing of electrons, and identical beryllium chlorine bonds will be generated by sigma spp bond formation. Sp hybridized orbital of beryllium will participate in the covalent bonding with p orbital of chlorine, so that here sigma bond origination called axial overlapping is possible, whose linear geometry is acquiring the bond angle of 180 degrees. So this is a clear description of beryllium chloride, where central beryllium is participated in sp hybridization of beryllium with a p orbital of chlorine. Sigma bond origination is possible in both the ends, so that a linear geometry with 180 bond angle. So this is the simplest structure of beryllium dichloride, linear. Now move on to boron trifluoride. In order to get the geometry of boron trifluoride and its bond angle and what could be the hybridization involved in this, first we have to go with its electron distribution, electron contribution within this boron. being it is atomic number 5, whose electronic configuration is assigned as 1s2, 2s2, 2px1. Here it consisting 2 plus 2, 4 plus 1, 5 electrons are present in the boron, and they are distributed in accordance with the above principle, 1s2, 2s2, 2p1. Now, this boron with the ground state electronic configuration 1s2, 2s2, 2p1, but in order to get 3 bonds with the 3 fluorine atoms, one of the electron from the s orbital will participate in the excitation in this manner, so that 2s orbital is acquiring 1 electron and 2p with the 2 electrons in the respected orbitals. After the excitation of this boron, by giving extra energy, this will participate in jumping of electron from s orbital to p orbital, so that we got 3 individual electrons which are responsible to share electrons with these 3 fluorine atoms. This is a required excited level boron electronic configuration. Right, it should form only one covalent bond to give boron fluorine bond, because if it is taken as such in the ground level. But in practical sense, we already saw that boron is surrounded by 3 fluorine molecules, 3 fluorine atoms. That's the reason why we are going to excite one of the electron from this s orbital to this p orbital in this manner, which is called the excited level. Now, it is forming 3 identical boron fluorine bonds around this boron. Here, 3 fluorine bonds are generated in the trigonal planar geometry. Sigma sp2 p sigma bond formation is possible by the axial overlapping of orbitals. Boron is associated with sp2 hybridized orbitals in the planar manner, and the fluorine, each fluorine is consisting one of the p orbitals, so that here p orbital of fluorine and sp2 orbital of boron will participate in the axial overlapping called sigma bond origination. Sigma p sp2 bond formation is possible in 3 possible directions. This is called a trigonal planar geometry. There is an intermixing of 2s orbital with the 2px and 2py orbital of boron. The redistribution of electrons are possible in order to get this sp2 hybridization, and these 3 lobes are separated by the bond angle of 120. Always planar, any planar geometry will acquire, that is the established kind of bond angle in between the trigonal planar geometry. Being boron with a trigonal planar geometry, always the consecutive bond angle will be taken as 120 degrees here. This is a kind of intermixing of s orbital with a 2p orbital, so that sp2 hybridization is possible with a trigonal planar geometry with a 120 bond angle here. Now, 3 sp2 hybridized orbitals get separated to have the minimum repulsive forces. That minimum repulsive forces will be afforded by taking 120 bond angle with respect to the central atom boron. sp2 hybrid orbitals which are acquiring each 1 electron in each lobe of sp2 hybridized orbital, these will participate in the mixing or sharing of electrons with the fluorine atoms. 3 individual fluorine atoms are contributing 1 electron by each, so that here trigonal planar geometry will be afforded for the entire molecule here. The bond formation with the sigma sp2 and the p bond in between boron with the fluorine. Here is the kind of trigonal planar geometry. Boron is surrounded with the 3 fluorines in maximum possible separation. All the bond angles are equal in nature, and each bond angle is taken as 120 degrees. And this is a kind of Lewis dot structure representation. Fluorine being it is associated with 3 lone pair of electrons, and one of the bond pair contributed towards the boron. Here is the representation of trigonal planar geometry in terms of Lewis dot structure. This is about the intermixing of orbitals and formation of boron trifluoride in the trigonal planar geometry form. And move on to another molecule. So till now we discussed about how the boron trifluoride molecule got generated. Boron trifluoride is a trigonal planar molecule, and the bond angle will be 120. Participated in SP2 type of hybridization, and the geometry is mentioned here. Now we forwarded into another molecule called ammonia. Ammonia molecule where nitrogen is a central atom which surrounded with 3 hydrogen atoms in their regular tetrahedral geometry. Actually, tetrahedral geometry is assigned for this molecule, but there is a certain kind of repulsive forces will be operated. That's the reason we will experience some extent of repulsions. some extent of distortion within the molecule. Let us see how it is possible. In order to explain this, nitrogen with atomic number 7 and electronic configuration is assigned as 1s2, 2s2, 2px1, 2py1, 2pz1. Already we have 3 electrons which are sufficient for 3 bond formations with a hydrogen. But s orbital is also constituted. So this s and p, 2s and 2p orbitals collectively regarded as a valency shell. So it is outermost shell, but here 2 electrons got paired initially, and p orbitals are with the unpaired electrons, which are clearly distributed in this energy level diagram of nitrogen, where 1s2 orbital with the 2 electrons in the opposite spin, 2s2 orbital also with opposite spin, and 2px, 2py, 2pz orbitals are contributing one electron in each orbital. So here is the energy profile diagram for the nitrogen electronic configuration, right? So here atomic energy level diagram depicted that here 3 electrons are responsible for the bond formation with the 3 hydrogens. Now let us see how can we apply this hybridization for this. 1 nitrogen atom, 3 hydrogen atoms are present in the ammonia molecule. NH3 is regarded as ammonia molecule. All the 3 NH bonds are assigned with 107 degrees 48 minutes. In general, when any molecule participating in SP3 type of hybridization, that should produce 109 degrees bond angle. Instead, ammonia, there is a certain distortion, certain contraction in the bond angle. Instead of 109 here, 107 is the experimental or calculated value given for this ammonia molecule with 1s2, 2s2, 2px1, 2py1, and 2pz1 electronic configuration. Then we are going to discuss why there is a change in expected bond angle. In order to get that, first we have to know what is the hybridization involved in this. Nitrogen atomic number will be 7, and 1s2, 2s2, 2p, 3 will be the electronic configuration. It will participate in SP3 hybridization. 1s orbital got mixed with the 3p orbital, so that SP3 hybridized orbitals are generated. And after mixing, these 2 electrons will become non-bonding. Why? Already 2 electrons is the maximum limit for the orbital, right? So further electron addition may not be possible. That's the reason the remaining 3 electrons will participate bond formation with the individual 3 hydrogen atoms, so that they are contributing 1 electron each, and mutual sharing is possible with the 3 electrons. So here formation of pyramidal geometry, pyramidal dimensional shape is possible. For this nitrogen, here lone pair of electrons are assigned here, and 3 unpaired electrons are accompanied by 3 hydrogen atoms, which is mentioned here. This is the system called a pyramidal shape. Okay, so here, because one of the corner occupied by lone pair, these are not participating in a bond formation, so that this is called a non-bonding electrons, right? So here, in general, if only this p orbital will participate in the bond formation directly, the bond angle expected should be 90, but observed value will be 107, and tetrahedral bond angle is 109. Then what could be the reason for this 107 bond angle irrespective of 90 and 109? So why this kind of deviation is observed? Why it is acquiring this 107 degrees 48 minutes bond angle? Let us see how it is possible. So here, in order to get sp3 hybridization, 1s orbital got intermixed with the 3p orbital, so that here tetrahedral geometry got assigned. In general, tetrahedral geometry should give 109 degrees 28 minutes of bond angle. So here 4 sp3 hybridized orbital should get this one. But in the practical sense, instead of 109, observed value is 107 only. This is the expected value, but observed value is 107 only. In order to explain this one, ammonia should be 109 degrees because it participated in sp3 hybridization and acquired by the tetrahedral geometry. And but it is experiencing a lone pair bond pair repulsions within the molecule. This is the main cause for the deviation from the expected value. So here, lone pair of electrons which are present with repel with these bond pair of electrons. If this hydrogen is moving forward towards this lone pair of electron, there will be a lot of lone pair bond pair repulsions. In order to minimize those repulsions, they are moving somewhat shrinking. Bond is shrinking towards the bottom side, so that here angle expected is 109, but it is somewhat reduced because in order to minimize the repulsive forces, it became 107 degrees 8 minutes. So that is clearly depicted here. This is the kind of system with the bond pair of electrons in between hydrogen and nitrogen. This is called bond pair, and the nitrogen only with the non-bonding electrons, these are said to be a lone pair of electrons. The main reason for the deviation from the expected bond angle will be bond pair, lone pair repulsions are observed. This is the main cause for the contraction in the bond angle. So this is observed value 107. That purely because of bond pair, lone pair repulsions. So this is about ammonia molecule. Now we are going to discuss about water molecule, and this is also clearly explained where this explanation was failed by previous theories. That's the reason why valency bond theory, we can say it is somewhat advanced theory of chemical bonding, because even though they are tetrahedral in nature, they should give 109 degrees bond angle, but rather they are producing 104 degrees bond angle for this water molecule. That deviation clearly explained by this advanced theory called Valency bond theory. We will go in detail about this concept application towards a water molecule, oxygen with 1s2, 2s2, 2p. 4 electronic configuration when it will participate in the SP3 type of hybridization, intermixing of s orbital with the 3p orbitals are possible, so that here SP3 hybridized orbitals are originated within the molecule. Only 2 lone pair of electrons, 2 unpaired electrons are available for bond formation with the 2 hydrogens, so that here 2 electrons will participate in the bond formation in this manner. 2 lone pair of electrons are said to be a non-bonding, and the remaining 2 will contribute towards the mutual sharing with 2 hydrogens, so that here water molecule is acquiring tetrahedral geometry in this manner with the 2 lone pairs and 2 bond pair of electrons. But there is a slight deviation. If we are expecting these 2 are the pure p orbitals, the consecutive angle should be expected as 90. But practical sense, it is taken as 104 degrees with 95.7 picometers of bond length, right? 104 degrees 5 minutes is the bond angle. Expected will be 109, but observed will be 104 degrees bond angle is possible. What could be the reason for this one? In order to explain this one bond angle for the water molecule, here you can clearly observe one lone pair of electron in either lone pair of electron, here bond pair with the hydrogen in either bond pair with the hydrogen will be there, and the consecutive angle is taken as 104 degrees. This is an exceptional condition. So that is purely because of lone pair repulsions are possible. So adjacent to lone pair will participate in the repulsion. Always like charges will repel. That's the reason where repulsions are possible in between. And in either reason is also there, one bond pair with this lone pair, in either bond pair with this lone pair is also possible. Both the kind of forces will operated within the molecule because of high steric strain. 2 kind of steric strains are possible. One is lone pair repulsion. Second is bond pair lone pair repulsions. Both the kinds are operated within the molecule. That's the reason why expected value 109, but observed value is 104 only. Within the ammonia molecule, only bond pair lone pair repulsions will be operated. That's the reason why shrinking will be somewhat less, that is 107. But within the water molecule, there are 2 forces are operating. One is lone pair, second is bond pair, lone pair. Both are operating within water molecule. That's the reason why shrinking is still larger. Always lone pair repulsive forces are higher, later bond pair, lone pair, and the least will be bond pair kind of repulsions. That's the reason why water molecule is acquiring bent shape. We can say 2 lone pairs are highly repelling. That's why shrinking of bonds are still higher. So that here bond shrinking to give 104 degrees 5 minutes as the bond angle observed, rather than this 109 degrees 5 minutes. So this is the main reason for the contraction in the bond angle. 2 forces are operating. One is lone pair repulsions. Second is bond pair lone pair repulsions. 2 kind of repulsive forces are operating. That's the reason why it will become 104 degrees. Now, so this is a clear description about the water molecule, where oxygen surrounded by the 2 non-bonding electrons and 2 Bonds with the hydrogen atoms contributing mutual sharing of electrons in the bent model with a 104 degrees bond angle, and it is clearly depicted in this Valency model too. Here 104 degrees 31 minutes is assigned for this water molecule, and they will participate in the sp3 kind of hybridization. Two orbitals are becoming non-bonding. Remaining two orbitals will participate in the covalent bond formation with the hydrogen atom s orbitals. And this is a clear description. Expected value will be 109 degrees, but observed value will be 104 degrees in the water molecule, being it is a bent molecule. Here bond length is given as a 95 degrees, 95.7 picometers. This is clearly because of lone pair, and lone pair bond pair repulsions. By this, we completed valency bond theory and their consequences. That means application oriented part of valency bond theory for various molecules, why they are deviating from the expected value. So all are clearly explained. Hope this session will be helpful for your preparation. Thank you very much for your consistent listening. Thank you one and all.